Hey, we'll take a look at encryption schemes. We'll introduce a little bit of a twist for encryption schemes. Namely, we will introduce weak messages. Weak messages are messages where the encryption isn't as strong, let's say. And we will then take a look at whether or not they are still CPA secure. Basically, we're doing most of this in order to understand CPA security a little bit better. So let's start with the first scheme. I call it a scheme with a weak message 0. We start with a CPA secure encryption scheme pi, and then we define our new maybe CPA secure encryption scheme pi prime, saying that the key generation is the same as in the original. The decryption is the same as in the original, but for encryption, we do a case distinction. If m is not equal to 0, it's the same as in the original. However, if m is equal to 0, then we will encrypt this message with the standard or with the normal encryption mechanism, but we will use fixed randomness. So as randomness, we will just use the 0 string. Okay, meaning that in this encryption scheme, 0 is a weak message, because if we encrypt 0, we will always get the same ciphertext for it. Whereas, because pi is a CPA secure encryption scheme, if we encrypt any other message multiple times, we would get different ciphertexts for this message. Let's first take a look at the CPA security game. Again, this game is between a challenger and an adversary. The challenger will first generate a key. Then in the next step, the adversary will be allowed to ask the challenger for several encryptions of plaintext that he chooses. So essentially, he will ask the challenger, hey, please give me the encryption of P1. And then the challenger will answer with encrypt of P1 using the key that he chose in the first step. Then A can look at the ciphertext and then maybe decide, hey, I want to know an encryption on P2. Then ask for the encryption of P2, C will reply with the ciphertext, etc., etc. Eventually, A will be done with all of this, and A will just output two messages, M0 and M1, which have the same length. Then C will choose a random bit and encrypt one of the two possible messages and send the ciphertext of that encryption to A. Then A is again allowed to ask for more encryptions, as in the second step, and eventually A outputs a bit B prime, and he wins if this bit B prime is equal to the bit B that the challenger chooses. So the idea is that A needs to guess which of the two messages were encrypted in C. We've already seen in the lecture that in order to fulfill CPA security, an encryption scheme must be probabilistic, meaning that a deterministic encryption scheme has no chance of being secure in this model. Why is this? It's pretty easy to see, because after A sees the ciphertext on either M0 or M1, he is still allowed to query for encryptions, meaning that he can in particular ask for an encryption of M0 again and then an encryption of M1 again. And well, then he has the two unique encryptions of M0 and M1, and he can just check which of these two C is. And then he just knows which one was encrypted with probability 1. And the way around this is to use probabilistic encryption, meaning that essentially it won't ever happen that you will see the same ciphertext twice. So this attack that I just described doesn't work anymore. So getting back to our weak message security scheme, something may be afoot here, because now for at least one message, we encrypted without any randomness, essentially. So we're using the fixed randomness, so there's no randomness involved anymore. Another question to you is this scheme with a weak message, is this CPA secure or not? And I give you a little bit of time to think about it. Actually, I won't give you any time to think about it. You can just pause the video and I will just go on. So yeah, this is not a CPA secure encryption scheme, which is easy to see if we can construct an adversary that can exploit this weak message in order to win the CPA security game. I write it down here. And this scheme is, this adversary will always just win this game. Why? Well, he knows the one single ciphertext for 0. Then the two challenge messages that he chooses are 0 and let's say 1, it doesn't matter. And then he just checks whether the ciphertext he gets, the challenge ciphertext is the same as the ciphertext for 0. If it is, then he outputs 0, and in that case he would win, because then it definitely was an encryption of 0. Otherwise, he will output 1, in which case he will also win, because if C is not equal to C prime, it must be the ciphertext for 1. So the probability of this adversary A winning this game is just 1. Okay, now let's take a look at a slightly different encryption scheme. In this one, we still have a weak message. However, this weak message is now the secret key K. So this will make things a bit more interesting. So if the message that I'm encrypting is the secret key K, then the encryption happens with randomness 0. Otherwise, I encrypt all other messages properly. So what do you think? Is this one CPA secure or no? Okay, did you think about it? I will solve it now. It is indeed CPA secure. The intuition for this is because the weak message is the secret key K, a PPT adversary shouldn't be able to find this message at all. So let's prove this. Let's prove that this encryption scheme is actually CPA secure. And the proof idea will basically be that this pi prime encryption scheme that we have constructed, it's almost the same as the secure encryption scheme, except in those cases where an adversary actually queries for the secret key. But those cases should be really rare, because, well, then you find the secret key. So we can just analyze it like this. So what is the probability that this PPT-A is able to break our encryption scheme pi prime prime? So to be more precise, what's the probability that adversary A wins in the CPA game against pi prime prime? And here we can do basically the standard trick. We'll do a case distinction. We will look at the one case where at some point A will query for the secret key, or one of the challenge messages is the secret key, and the other case where he does not. Okay, we will call this event finds key. So we can write this probability as using the law of total probability as this kind of case distinction. So here on the top we have the probability with the case that he finds the key, and here the probability with the case that he does not find the key. And now we can notice two things. One is that the probability that he will ever find the key, this should essentially never happen, because it's a secure encryption scheme. So the probability of him ever finding the key should be negligible. The other thing we can see is that the finds key event does not happen. Then looking at this here, we can essentially replace pi prime prime with just pi. Because if finds key does not happen, then pi prime prime will never encrypt the secret key, or the adversary will never see an encryption of the secret key. And then those two schemes are the same, right? Because if you remember, those two schemes by definition are just the same then. And then we can make all of this a bit easier for us, because we can notice that if we replace this equal with a smaller equal, we can make these probabilities a little bit larger, but easier to analyze. In particular, because this finds key here is already really small, it doesn't really matter that we're making this whole probability even smaller by adding this win probability event here, meaning that we can just remove this, make the probability larger, but still, because finds key should almost never happen, small enough to be useful for this proof, right? And then in the next line, we can also do a similar thing. We don't actually care how likely it is that he does not find the key, because him breaking or him winning against the encryption scheme pi should already be not more likely than 1/2. So we can also just remove this from the probability. And then we're left with the probability that he finds the key and the probability that he wins against the scheme pi. Okay. Then we know that this part here is negligible by assumption, because the original encryption scheme pi was of course secure. And we're just proving that our weak message doesn't change anything about this in pi prime prime. And this event here, that he finds the secret key, that's also negligible. We actually have to do a reduction for this in order to prove this formally. But I won't go through the details. The idea here is just, if we had an adversary A that actually, so that this event here, the finds key event, that this was not negligible. Okay, so you would have a larger chance of finding the key at some point and querying it to its challenger. Then we would be able to construct an adversary A prime. A prime would internally run A, just answer all of the encryption queries as with its own challenger against the encryption scheme pi. Then the adversary A prime that we're constructing will just hope that at some point the adversary A will trigger this finds key event, meaning that A will just hand the secret key to our adversary A prime, and then A prime will just use the secret key to break the security of the encryption scheme. Okay, at this point it's easy then, because you can just decrypt a challenge ciphertext, right? One small problem is that we actually, the adversary A prime won't know which of the queries that A does will be the secret key, because it doesn't know the secret key. But there are ways around this that we'll see later in the lecture. Yeah, so this is just a rough sketch. Essentially, what I'm saying is that this here is also negligible, and this actually needs to be shown via a reduction, which I'm not doing here. Okay, but then overall, we have seen that the probability that A wins against pi prime prime is just negligible. Because if I add up two negligible functions, then the result will still be negligible. Oh, one small correction. This negligible here is not actually true, right? Because the probability that A wins the CPA game against the secure scheme pi prime is not actually negligible. It's 1/2 plus negligible. So actually, yeah, this is negligible plus 1/2. And then this down here would also be negligible plus 1/2, which is also what we would expect for the CPA game against pi prime prime. Then there are also normally used absolute values for the stuff in between, but yeah, I'll just leave them out for now. So overall, we've seen that weak messages are not a good thing, obviously, but if the weak message is somehow related to the secret key enough, then it doesn't actually make a difference, because nobody would be able to find the weak message at all. Thanks for watching, and see you.